Hi class, I just wanted to work through any problems we didn't get a chance to do together in class and really show you the step-by-step solutions. So we actually switched things up a little bit and spent more time working on the R8 topics and less time working on section R2. However, R2 really is important, not to de-emphasize that. Those are properties that we definitely are going to need to know and know well if we're going to be successful doing some of these topics that we're going to see later on. So section R2, the part of it that we were interested in covering is the property with respect to powers. So we did spend a little bit of time talking about what it means to have a power, that when we write a base value raised to a power, it means you're repeatedly multiplying that base value, whatever that quantity of times is that you have for your power. And then we talked a little bit about the special kind of definition that any base value raised to the 0 power results in a 1, and then how we handle negative powers is by reciprocating the base. So that negative power means to reciprocate your base number. So we talked a little bit about, like, for instance, on this 3 raised to the negative 2 power, we have to take care of the negative 2 power first, so we would reciprocate the number. So I can think of it as 3 over 1 to write it in a fractional form. And then when I reciprocate it or flip it, my 1 goes on top, the 3 goes on the bottom, and then my power can become now a positive power of 2. So how do I calculate 1/3 raised to the second power? Well, the second power means whatever my base is, even for 1/3, I'm going to multiply it by itself that 2 quantity of times. So there's 1/3 squared. It's 1/3 times 1/3. And then this is the multiplication of fractions. So you multiply across the top. 1 times 1 is 1. 3 times 3 is 9. So there's 1/9 for us. That is our final answer. And then in example B, we looked at the instance of 1/3. So if it's already a fraction, again, you still handle the negative power. So we've reciprocated the 1/3 to create 3 over 1. That would be now raised to the positive power of 2, since I've dealt with the negative power part of it. And then we squared it by multiplying it by itself, which got us 9 over 1, or the value of 9. And then here, maybe we'd be kind of stumped looking at C. This goes back to that definition that any base value, even 5, raised to the 0 power is a value of 1. So that was just automatically 1 right there. Then in the next bit, we looked at laws of our exponents. And so we looked at the 5 different rules there. And what I didn't cover with you is this example that we had. So usually most students are fine with our 5 properties that come up, or the laws of exponents. Where they have difficulty is when they all come together. So usually when you use these, you're using more than one property at once, and that's where things get tricky. So here you just want to be careful and be really mindful of which property you're using and what that property does with your powers. So when I first look at example A, I might be tempted to add up my powers because it kind of looks like property 1. However, it isn't really, because I have 2 different bases here. I have a base of x, and I also have a base of y. So I can't use that first property there because they're not the same base. Same thing on my other set of parentheses. So really the only thing that I can do is actually perform the multiplication of these 2 quantities. So how do we multiply them? Well, we're going to multiply kind of each part of it. I'm going to multiply the 4/3 times the negative 9. And we'll multiply the x squared with the x to the negative 4. And then multiply the y to the negative 3 power and y to the 5 power. And I kind of artificially put those in parentheses just to kind of see each individual piece multiplying. But we don't really need the parentheses there, since we know that this is overall one big multiplication problem. So when I multiply my numbers, we can treat this in many ways just like we did in our previous section. I can think of negative 9 like a fraction by sticking it over 1. And I can also write it as a factored form. This is 3 times 3. And why that's helpful is because fractions are hard or difficult to calculate because of the denominators. So if I get rid of this denominator 3 by canceling a like factor of 3 on the top, that makes things a lot easier. So that's why I factored the 9, so I could get rid of those common factors of 3 on the top and the bottom. So now this becomes a lot simpler of a problem to solve. It's really just 4 times a negative 3, which is negative 12. So that's one way that you can work through multiplications fractions easier, even if they're numerical and not algebraic, is by writing out the factors. You could have also just typed this into a calculator too and looked at your answer that way. Now I can look at my x's. So now I have the same base. I have x and x, so that fits this first law of exponents. So I would keep the x, but I would add the powers of x. So this would be raised to the power of 2 added with negative 4. And I wrote that out explicitly just because we're talking about what's happening. But really probably what I would do is not write that out. I would actually perform the addition and just write the result. So 2 plus a negative 4 is a negative 2. So if you understand the property well enough, you don't have to write that in between step. That is totally fine. And then y's, here I have the same base of y and y. So again, that's property 1. So I'd have y raised to the negative 3 plus 5. So that would be y to the positive 2 power. Now here, I would like to circle this and say I'm done. However, if you notice, they have the statement express the answer so that all exponents are positive. And that's important because a negative exponent in its own way is kind of like an operation that can be performed. We can reciprocate it and then write our power as a positive. And that's what we want to do here, because to really simplify means you've done all the math that you can. And I haven't done all the math I can if I wrote a negative power. So I'm going to handle this x to the negative 2. So what I can do with that x to the negative 2 is I can think of my expression as an overall fraction. Think of it as like being over 1. And then I can go ahead and reciprocate this x part and move it essentially to the other part of the fraction. So when we reciprocate it, we're really moving that part or that term to the other part of my fraction. So right now it's in the numerator. So to reciprocate it, it would go to the denominator. So I kind of think of that as pushing that term to the other part of the fraction and then allowing the power to go positive. So that x to the negative 2 is getting pushed to the denominator, and y is becoming a positive power of 2. Or sorry, x is becoming the positive power of 2. Y already has a positive power, so it can stay in the numerator just fine. So there is our result. All right, so that's using some of our properties. Some other things we talked about is how to evaluate our roots and how our roots kind of fall into the same ordering as PEMDAS. So the first several roots we did were nice square roots, so we call perfect squares, or perfect square roots, because they square root to be nice whole numbers. So 121, what I'm really asking myself here is what times itself yields the value of 121. So in this instance, 11 does that. 11 times 11 is 121. So I could just type that right into my calculator, or I can kind of go through that process of figuring out what the two things are that multiply and create that value. That process is helpful when it's a nice whole number like 11, but if it's not a nice whole number, then that's where things get a lot more difficult. So there we just calculate our root. The next example is really letting us acknowledge that we can break up our square root over our fraction and just square root the numerator part and square root the denominator part. So the square root of 16 is 4. And the square root of 49 is 7. So the whole square root of the whole fraction was really just 4/7. So that's a very useful thing, is you can break up the square root over the division. And then in C, we were looking at where the root fell in our PEMDAS, and really the square root falls in the same position as an exponent. So I would do the square root first before we do the multiplication by negative 5. So we calculated the square root of 36 to be 6, and then we can perform our multiplication, and this becomes negative 30 as a final answer. Example D, I may be tempted to subtract the numbers underneath the square root and say this is like a negative 72, root 72, but that would be incorrect, because these values are kind of isolated underneath their roots. We have to calculate the square root first, right, because it's like an exponent, before I can do the subtraction between our two terms. So we got to calculate this first. So root 81 would be the square root of 81. That one I don't know off the top of my head. Let's look at that. So if you're not sure, you can always type it in. I mean, that's why you guys have access to scientific calculators on exams. That's 9. And then square root of 9, that's 3. So I'd calculate that first and then perform our subtraction. 9 take away 3 is going to get me a final answer of 6. And then E, we talked a little briefly about the fact that when you have multiple things underneath your square root, that it's kind of like an implied set of parentheses, that we have to calculate what that value is before we can use the square root or perform the square root. So I would treat the stuff underneath my root as kind of like its own PEMDAS. So before I can do subtraction, I got to do the multiplication step. So 64 minus whatever the result of 13 times 3 is. 13 times 3 is 39. So now I can perform my subtraction. And what is that one? 64 minus 39, 25. And that worked out really well because the square root of 25 is 5. So we're still following PEMDAS. Just be aware that your roots work like an exponent, so that would be when we do that. And then if there's multiple things underneath your square root, that you have to perform those operations first. And then kind of like what I was showing you guys on the other page, knowing how to use your calculator is immensely helpful. And the tricky part is that all calculators may have kind of different buttons or different locations of buttons or different ways that it wants you to type in your results. So knowing how to type in powers on your calculator is very important, and also knowing how to type in roots would also be very important. So these are two things that if you don't know how to type them into the calculator that you intend to use on your exams, so whatever scientific calculator you're using, you definitely want to learn and find out from me how you would do that. So those are two things that we want to be aware of, and I can't really give you hard and fast instruction as to how to do it because everybody's calculator is a little bit different. You know, even two different Texas Instruments, you know, Texas Instrument is one of the makers of a calculator. Even two different models from the same manufacturer type things in a little bit differently. So whatever calculator you plan on using, make sure you know how to use it or come talk to me. And that finishes up what we talked about in section R2. Section R8 is very, very similar, except instead of talking about powers per se, we're talking about roots. But what we're seeing is a lot of the properties of powers also work for roots. And so there's a lot of overlap in those two topics. So we looked at how to type in roots into a calculator and the fact that when you're doing an even root of a negative number that you get a non-real result. So we just consider those not real numbers and leave it there. But odd roots you can calculate even if the value is negative. And then we talked a little bit about how some of our rules applied. So this is kind of like that product property, right? Kind of going reverse here. If I do the root of two different items, we can break up the root. Same thing with division, and that the order that we apply the power in the root can be done in either order. So we looked a little bit at simplifying these roots. And then also the fact that as long as we have like roots, so they have the same type of root with the same thing under your root, that you can add them up essentially just like terms and adding the coefficients. So we looked at that, and we talked very briefly about rationalizing, but we still have to finish rationalizing these examples. So I did the first one for the square root of 3. And in fact, all of these problems, we do not want our square root left in the denominator of a fraction. That's a big no-no. And so we have to do some work to fix that, and that work process is called rationalizing. So when we say the word rationalizing, we're essentially saying do the math you need to get rid of the square root in the bottom of your fraction. So when I rationalized 1 over root 3, the trick is to use however many of your root that's causing the problem, the square root of 3 here, use those to help get rid of the root. So by multiplying root 3 by itself, I get a root 3 squared in the denominator. And that square root and power 2 undo each other, leaving the positive value of 3. So we're using that to our advantage here. I briefly talked about how you would adjust for having a binomial. So here I have two terms in my denominator. The root 2 is causing the problem. However, just multiplying by root 2 doesn't fix things. So just to give you guys a for instance, let's say I had I don't know, something over 2 minus root 2. if I try to pull the same trick that I did for a and just multiply the root 2 on the top and the bottom, that's not going to fix things, because on the bottom that becomes a distribution problem, right? I would distribute the root 2 and I would get 2 root 2's minus the root 2 squared. So it would fix my root 2 for the second term, but then it would recreate another root 2 on the first value. So it doesn't help me get rid of the square root of 2 entirely. So it's not enough to just multiply the root in a case like this. We have to take into account both of the terms in the binomial. So how do we fix that? Well, we multiply by what's called the conjugate, right? So these guys right here, I should write that, are called complex, or no, not complex, pardon me. They're just called conjugates. C-O-N-G-U-G-J-U-G-A-T-E-S. Conjugates. And essentially what makes them conjugates? Well, they have the same values, but what was subtraction between these first two terms, I use the opposite value, the plus on this other term. And what this really is creating is the difference of perfect squareds, if you look very carefully. And so when I FOIL these terms, I would have 2 times 2, which is 4. I wrote that down already. The outer set of terms would be just 2 times the square root of 2. And it would be positive on the outer terms. For the inner set of terms, I have a negative 2 root 2. And on the last set of numbers, I would have a negative root 2 squared. So, I mean, it looks more complicated. But what is actually happening there is my 4 would stick around. The 2 root 2 and the negative 2 root 2, those add to 0, so those would go away. And then the root on the 2 would also get taken care of. So I would have minus, my root and power 2 cancel, leaving just a 2. So this whole denominator, once I perform all my mathematical operations, is 4 minus 2, which is 2. So the denominator, by multiplying by the conjugate, it gets rid of the root, and that's what we were wanting. However, I have to balance that, right? I can't just multiply the bottom by this, new statement. We need to make sure that we balance it by multiplying the same thing on top of our fraction. So I'm not really changing things. I'm just multiplying by a very fancy 1, right? When I did this 2 plus root 2 over 2 plus root 2. So I still have to multiply the top. So this is also a distribution problem. I can distribute the 3 through, the root 3. So 2 times root 3, here I have a value of 2, but that doesn't have a square root, and the root 3 does. So how we handle that is they're not like items. You can't really combine them and say get like a root 6 or something. The best I can do, since they're different things, is to just write it as a default multiplication. In many ways, just like if I'm multiplying a value of 2 by the variable of x, the best I can do is write it as 2x. It's really the same idea. These roots can only change or have math happen on them when you multiply them by another root of the same kind, right? So that was the first term. The second term, that's the situation where we have a root times a root. I have a square root of 3 times the square root of 2. So that would be plus the square root of 3 times 2 underneath the root, right? Instead of writing it as 2 separate roots, I wrote it as a single root. So this would be 2 root 3 plus, I can now perform the multiplication of 3 times 2 and get a root 6. And now these are not common roots. They both have a square root of 2, or square root 2, square root, but this is square root 3 and this is square root 6. They're not like roots. So I can't do anything with that. I have to write them as separate terms. And so that would be essentially my final answer. I could write it as one big fraction. I could also break up my division if I wanted to and let each term get divided by the 2 because it's a monomial. I can actually do that. And that would maybe allow these 2's to cancel out or reduce down to just a root 3. But it doesn't really help me with the 6 because the 6 is stuck under the root. So I can't divide it by 2 because 2 doesn't have a root on it. So the best I could do is just leave it. So you could really write your answer either way. It's just completely a formatting issue, whether you like one big fraction or 2 separate fractions. And then the last example, I wanted to show because it's not a square root, it's a cube root. But the idea and the premise is the same. I'm going to multiply by the root that's in the denominator until I'm able to get rid of it. So for a square root, you only had to multiply it one extra time. Here, I need to multiply it 2 extra times. And let's see why. Because if I were to multiply an additional 2 times, then in total, I would have 3 of the same quantity, this cube root of 9b squared, which is the equivalent as a power of 3. And that's important because that power 3 undoes the cube root, and that would just leave us with whatever the underneath the square root symbol. So this would be just 9b squared. So the most important thing is I got rid of that root symbol in my denominator, and that's exactly what we're trying to do here. So if I say I had a 4th root, I would have to make sure I have 4 total roots in the denominator to cancel out our root symbol. If I had a 5th root, not that it would ever happen because that's getting pretty big, but if I did, I would need a total of 5 of those 5th roots to multiply together. So it's continuing to multiply as many times by that same root until you get the root to cancel and leaving your denominator without a root. Now I fixed the bottom, but now I got to balance that by doing my multiplication on the top. So these are cube roots as well of the same quantity. And so now I can go ahead and multiply. The 6 doesn't have a root on it, so it stays out in front. The cube roots I can go ahead and combine, kind of like I did in my last step. I multiplied the things inside. I can also multiply the things inside on this one. So I can do the 9b squared times another 9b squared. And then we can simplify that. That would turn into the cube root. 9 times 9 is 81 with a b to the 4th. Now I'm not truly done because this cube root can go ahead and simplify, and you always want to simplify your roots if you can. So let me look at my factors here and see what I can take out of that cube root. So 81, I already know it was 9 times 9 from my previous step of work, and I can break down my 9s into factors of 3. And then on a cube root, how do you reduce a cube root? You look for a triple set of the same number. So I have a triple set of 3s. So what I can do, let me write down what's still there. So all these things still stay there. And then I'd have a cube root. So I can pull that triple set of 3s outside my cube root, but I would still have this single 3 that's going to need to stay inside my cube root. So that simplified the 81. For my b's, I have 4 b's. Since it's b to the 4th, I can create a single grouping of 3 of them. So that single b would come outside my cube root. And then I would also have a single b left over to stay inside. So that's how we would reduce our cube root. And then we just clean up any multiplication that's left over. So 3 times 6 is 18. I have a b there with a cube root of 3b. And I have 9b squared. So I'm not quite done just yet. This problem does go on a little bit longer because we do have many things we can simplify. I can simplify the 18 and 9. Those actually divide, leaving a 2. And I can also get rid of one of the b's. I have a b on top and a b on bottom. So we can cancel one of the b's, leaving a single b on the bottom. And then the cube root of 3b has to stick around. I know it's very tempting to cancel another b, but my b is underneath the cube root, and so I can't do anything with that because it's trapped underneath the cube root. So that's really the best we can do there, is to leave it like that. And let me actually move my 2 over so there's not quite such a big gap there. And that's it. That's all we can do. All right, and then the last little topic we want to talk about is what those fractional powers do. And I previewed a little bit in class how a fractional power can mean the same thing or be equivalent to a root. Now we're going to be a lot more explicit about that. So a raised to the power of 1 over n, well, that means that that denominator, the n, is the type of root or the index of the root, and then a is the base. So the nth root of a is equivalent to a raised to the 1 over n, where the index is the denominator of your fraction. So then say I had, not just 1, but I had some other value in the numerator. Well, that's just a normal power. So it's like a raised to the power of m, and then the nth root is applying. And one thing we kind of mentioned too is that the order that we do the power or the root can be interchanged. So here I did the power of m first and then applied the root, but I could have also done the root first and done the root nth root of a and then followed that up with the power of m. And it works either way. It's really entirely based off of the problem and what might be the easiest route to go in terms of which order that you actually apply it in. So let's try a couple of those problems. So here I want to rewrite each of these with that fractional or rational exponent on it, and then of course reduce it if I can. So the cube root I can rewrite as the power of 1 over the index, which is 3. So it's like 1/3 of 6x. And then to reduce it, I can go ahead and treat this like any power, whether it's a fraction or not. You can apply the power to each factor individually. So this is like 6 to the 1/3 times x to the 1/3. And that's really all that you can do. I don't have any other math I can do on that. So that would be the best that we can do. Now in the next one I can see I have power 3 and the 5th root. So that 12c I can convert into 3 being in the numerator for the power 3, and then the root index 5 being in the denominator. So it's like this equivalent to the 3/5 power. And then kind of like on the previous example, if I wanted to go ahead and use that power rule where it distributes through to each item, I can do that. So this would be 12 raised to the 3/5 and c raised to the 3/5. And that's all that I can do there. And then the last one, same idea. I can rewrite this whole base. In this case, it's 2xy is my base. The power becomes the numerator of our fractional power, 5, and the root becomes the denominator. So it's like this whole fraction raised to the 5/6. And then again, if I wanted to, I could go ahead and apply the 5/6 to each part. So 2 gets a power of 5/6, x gets the power of 5/6, and y gets the power of 5/6. All right, and that's it.